So after discussing about specific heat, latent heat of melting, latent heat of vaporization, and then we have discussed about different modes of heat transfer in the previous discussion. So different modes of heat transfer are like conduction, convection, and radiation. Okay. So as you said, conduction it requires a medium, whereas the radiation it does not require any medium. So the transfer of heat from sun to the earth, if there is, even though there is vacuum in between, still there is transfer of radiation energy, which are nothing but the electromagnetic waves. Okay, so and we have discussed also about convection. So in convection, there are two types of convections we have discussed. One is like the natural convection, and the other one is the forced convection. Okay, so the boiling of water by using some heat source, that is natural convection. But when you are using any pressurized air, suppose you are using a room heater or a blower to blow air into a cold room, or so the another practical and beautiful example is the pumping of blood by heart in our circulatory system. So the blood is being pumped by our heart, and it moves to different parts of the body and maintain the body temperature constant throughout. So that is one example of forced convection. Okay. So conduction, as we have studied that heat transferred is equal to K A delta T divided by L. So K is the thermal conductivity, A is the area of cross section of the rod, delta T is the temperature difference between two ends between which the heat is getting transferred, and L is the length. So more is the distance between two points between which heat is getting transferred, lesser is the heat transfer. So, and in radiation, we have discussed about various things. We have discussed about black body radiation. We have discussed about mm, Wien's displacement law. We have discussed about Newton's law of cooling. There, there Newton's law of cooling, and then uh, we have discussed about black body radiation, Wien's displacement law. So there are some important things in Wien's displacement law. There are some important things in Wien's displacement law, like lambda m into T is equal to constant. From that concept, how we arrive at the how we measure the temperature of celestial bodies like moon and sun. That also we have discussed, and also we have discussed how we measure the wattage of electric bulb, how much heat is transferred from a human body. So all that concept, all that concept related to radiation we have discussed. Okay. So after covering the heat transfer, the specific heat, the latent heat, and all those concepts, so the next chapter is related to thermodynamics. Okay. So there are various laws in thermodynamics. So we start with zeroth law of thermodynamics. Okay. So what is zeroth law? So zeroth law of thermodynamics is uh, when two systems in thermal equilibrium with third system separately. So if two systems are in thermal equilibrium with a third system, suppose two systems A and B are in thermal equilibrium with system C, That means, and separately. So A separately is in thermal equilibrium with B. A separately in thermal equilibrium with C. B separately is in thermal equilibrium with C. That means system A and B are in thermal equilibrium. Okay. So that is a simple law, zeroth law of thermodynamics. Then we come to the first law of thermodynamics. Okay. So first law of thermodynamics is nothing but it is called law. It is an extrapolation of law of conservation of energy. Okay. So the state of a gas we define by pressure, volume, and temperature. Okay. So the gas uh, has some internal energy. Okay. So what is the internal energy of a gas is sum of its molecular potential energy and molecular kinetic energy. Okay. So as mentioned here, internal energy is equal to molecular potential energy plus molecular kinetic energy. We denote it by capital U. Okay. So, as I said, internal energy of a gas is sum of kinetic energy associated with various random motion of molecules. So, if you ignore the attraction between molecules, just which is negligible, if you can consider, then the internal energy of gas is nothing but the kinetic energy. Sum of kinetic energy means sum of kinetic energy of each and every molecule present in the gas. So, because every molecule in the gas is in the state of random motion. So all the translational or rotational motion, it has some energy associated with it. So if you sum the energy of each and every molecule, uh, if you sum the kinetic energy of each and every molecule, you can arrive at the internal energy of the gas. Okay. So, internal energy of a system can change through two modes of energy transfer. Two modes of energy transfer. So, how you increase or decrease the internal energy of the system? Either by supplying heat or either by doing some work on the surrounding or the surrounding doing some work on the system. So in this case, you can see this is a system. So you can see here you have a piston, you have a cylinder, this green color dots, this represents some gas is present in the system. Okay, and let us say you have some weight which is being supported with the help of some pulley, some weight is there, and you are supplying some external heat source. Okay, and let us say the state of this gas is, let us say, pressure, volume, and temperature. Okay, so if this is the condition, uh, then if you are supplying some heat, there are chances that the gas inside this, it will try to expand. Okay. So when the gas is trying to expand, then the system will try to do some work on the surrounding. So this heat, so so this so this heat So this V, so the system, it has P, V, and T. So if you are supplying some external heat, so which is nothing but your del Q. So you are supplying some del Q here. Okay, you are supplying some del Q. Okay, so this del Q can do two things. One is the external heat can either increase the internal energy of the system or it can increase the internal energy, nothing but the kinetic energy of these molecules, or it can do some work also. Okay, so it can do two things. So del U. So when you are supplying del Q, it can, it can, it can increase the kinetic, the internal energy, or it can do some work. Okay. Can do some work. Okay. So that work is nothing but we'll discuss in the next session. This work del W is nothing but your P into delta V. Okay. So what is this delta V? Suppose this piston moves from this position to this position. Okay. If you imagine this piston moving from this position to, let us say, this position, it is moving because you are heating and gas is trying to expand, and if that happens, this system moves from this to this. So when does this system moves from this position to this position, there are chances that you have some incremental increase in volume. So that incremental increase in volume is nothing but your delta V. Okay, and why it has unit of work? As you know, pressure, its unit is Newton per mm square, or normally this is nothing but your MPa or whatever you say. And delta V, its unit, if you put it in mm, it is nothing but volume mm cube. So it becomes Newton mm. Okay. So you know force into distance is nothing but your work done. So work and energy has the same unit, which is nothing but your, if it is Newton meter, it is joule. Okay. And as you know, rate of work done is nothing but your watt. So here, so heat supplied is equal to a change in internal energy plus work done. So that is the first law of thermodynamics. Okay. So next we will try to solve some numerical on the first law. Okay.